So thank you very much for the organizers for inviting me in this marvelous place. So the work I'm going to be talking about today has been carried out by Laure Bruin, Tino Cuben, who is in the audience, Matthew Desjardins, and all these people who are students in my group. And on the theory, we have collaborated with Audrey Cotter. So in fact, you will have some kind of déjà vu feeling with respect to what has been said so far. But I'd like to, let's say, reintroduce some of the things which have been already discussed to establish a common vocabulary, just to be sure that we're talking about the same things. So we're going to be dealing with mesoscopic quantum electrodynamics with carbon nanotubes. And so this is strongly connected to cavity quantum electrodynamics, which deals with the interaction between light and matter at the most elementary level, so down to a single atom and to a single photon. So this is an example which we particularly like in Paris, where you have a Rydberg atom coupled to a superconducting mirror cavity. And that's the, let's say, that's the on-chip version, which was pioneered by the Yale group. And these two systems, although they look very different, are to a great extent described by the same Hamiltonian, which has been already introduced several times today, which is the Jennings-Cummings Hamiltonian. And so here is the spin part, or the effective spin part. Here's the photonic part, and here's the coupling part here. And one particularly interesting regime is reached when this coupling part is larger than the dissipation of the photon in the atom. And thank you. And today I'm going to show you that sure, you can do this kind of things with carbon nanotube quantum circuits, but it can also be very interesting to go in a more, generic regime with carbon nanotubes, where essentially this kind of architecture will allow us to learn about many-body physics. And my favorite many-body physics problem is the Kontos problem. Okay, so what are our cavities which we're dealing with? These are coplanar waveguide microwave cavities. So this is a sketch of these cavities. So you have a central conductor with two ground planes, which is the central conductor has two cuts here, which are the mirrors of the cavity. And they have a fundamental frequency in the microwave range of about 6 to 7 gigahertz with quality factors of around like 15 to 20,000. Because they are made in niobium, which is a superconductor. And so the measurements are going to be carried out at low temperatures where this cavity is closed or in its ground state, essentially, if you do nothing to it. So what is the atom? Because they're in, so there is the cavity, the photonic part in cavity quantum electrodynamics. There is the atomic part. So in our case, there are going to be two kinds of atoms which we're going to be dealing with, depending on the kind of experiment which we want to do. So on the left-hand side, we're going to deal with closed quantum systems. And so essentially, in our case, the generic closed quantum system which we like to work with is a double quantum dot, where essentially you can store quantum information in the electron being on the right or on the left or the right dot, or even better, on the spin of the electron. And since it's spin Cavitronics, it's very well fitted to the topic of the conference. So this is more this is more quantum information oriented, this kind of setup. But there is a very interesting other setup, which is what we call the open quantum dot regime, where essentially you have a single level which is strongly coupled to the leads which you use for driving a finite current. And with this kind of system, you can revisit impurity physics of condensed matter. And our favorite impurity physics problem is the Kontos problem. So now, how do these two systems couple to the electromagnetic field? So here, since we're dealing essentially with a charge which is moving, the coupling mechanism will be electrical. And I'm going to show you that you can still do things to the spin and, in fact, employ a fourth path. So this morning we had like 3 paths. So we can employ a fourth path to couple a spin to the microwave field and keeping a very large anharmonicity of the spectrum. And so essentially, you have a coupling which is here, which can be described theoretically by this kind of term, and this is just an electrical coupling. Since we're dealing with charges which move over mesoscopic distances, we can expect to have very large dipoles over the order of 10 to 100 megahertz, even though there is a single electronic charge. And here, for example, here a single electronic spin which is moving in this kind of setup. Okay, and so the main reason why so many people work on this kind of hybrid circuit QED with quantum dots is essentially to transfer the ideas of cavity quantum electrodynamics, which have taught us how to probe, manipulate microscopic or macroscopic quantum states. We're using cavity photons. So we want to transfer these ideas to hybrid mesoscopic circuits and to quantum dot circuits, which hopefully a host can carry quantum information. So there are going to be two questions, two parts in this talk in which we will ask ourselves two main questions. The first is it possible to achieve the strong coupling with a quantum dot circuit, so down to an individual excitation, so an individual spin excitation or an individual electronic excitation. And the second type of question is, can we use that kind of architecture for addressing more condensed matter questions where you have many body effects which start to play a role? So, I mean, there are many papers, even very recent papers, which have addressed the first part of the question here, and a lot of advance. And I'm going to show you here what we did first in this part. So, in order to understand what is going on when you couple the cavity to these systems, it's interesting to see what the cavity allows you to measure. And in the two different limiting cases which we essentially will address. So first, let's say the closed quantum system regime. So in the closed quantum system regime, you can say that your system will have several transition lines, which will, so this is, for example, this green line here, which will be controlled by a control parameter. So this can be the magnetic field, but this can be the electric field, so the gates which we have on our system, which allow you to tune in or out of resonance with the resonator charge or spin transitions. And when you do that, and you can show from a linear response argument that essentially the cavity will feel the system charge susceptibility, which is expected to have at least one resonance. So this is the simplest case where I have a single resonance at omega double DQD. DQD is for double quantum dot because that's the simplest system you can imagine. And essentially the idea is that when, so it's very similar to what has been shown this morning for the Magnon coupling, except that here it's an electrical coupling. So you see that this is an input-output formalism, which allows you to show this Lorentzian line shape of the cavity. And this is the linear response, expectation, where essentially this shows you that whenever the cavity comes into resonance with the double quantum dot, you have a sharp feature in the amplitude or in the phase of the transmitted microwave signal, and this allows you essentially to directly map the low energy spectrum of your system as a function of the control parameter, because the cavity provides a cut of the hybrid double quantum dot system. So that's the closed regime. And in the open regime, you can also rely on a linear response argument. But physically, what the cavity does is that essentially it molds the electronic gas. So it shakes back and forth the chemical potential of the electronic gas, which means that it essentially pulls and pushes the charges so in and out of the electronic system. And even in the adiabatic regime, this provides a very different piece of information with respect to what you can get just from a transport measurement, because this is a direct way of measuring the compressibility of the electronic system. And especially when you have interactions, the compressibility is completely different from the conductivity. So I'm going to show you that this is going to be very interesting for the last part of the talk. Okay. So, but let's first ask to ourselves whether it is possible to achieve the strong coupling with quantum dot circuits. So you can try to couple strongly the charge, because the charge will provide you a large electric dipole. So this has been done by the group in a group of Jason Petta or the group of Andreas Wallraff last year. And you can also now couple the spin. A single spin. So in these two very recent papers, and we demonstrated the principle of this coupling in this paper here. And here this would be employing a fourth route. So keeping the intrinsic anharmonicity of a spin 1/2. So this is the most anharmonic system you can imagine. But shaping essentially the spectrum in order to have to engineer an electric dipole transition for a spin 1/2. And so how we do this is here to have a non-collinear spin valve, which essentially allows you to give an electric dipole to the spin. And with this, you can increase by 5 orders of magnitude the natural coupling, magnetic coupling, to a single spin by engineering this electrical coupling. Okay, but you can also do things which are different. You can try to ask whether it is possible now to play and to reach the strong coupling regime with other kinds of degrees of freedom. And in our case, one degree of one type of correlations which we like particularly are superconducting correlations, especially when they are non-local. Yes?
What about Snowden interactions instead of this inhomogeneity, just some natural Snowden interaction?
So thanks for the question.
Carbon nanotubes?
So the carbon nanotube, it's too weak, and essentially the idea is that if you plug in, if you have a material which has naturally spin-orbit interaction, essentially you will have built-in also relaxation mechanisms or decoherence mechanisms associated to the spin-orbit interaction. And so it might very well be, and in most materials, you cannot choose, let's say, the best part of the two worlds. Essentially, you have large spin-orbit interaction, means you have very short decoherence times. With this kind of scheme, which has been used in silicon here, you can use a material which has the best decoherence properties you can wish for, like if it's completely intrinsic, and engineer at will, and when you want it to be there, a finite spin-orbit interaction. And with this scheme, you can essentially have free lunch, because essentially you get a very, very narrow line width for the spin when you want to have a very narrow line width. For example, if you want to make a memory, and you can have a very high speed of operation if you want to make for example, a 2-qubit gate, for example.
You can control the normalizations.
No, here it's even easier if you can control the difference between the chemical potential between the left dot and the right dot. Because if you completely localize the dot let's say on this, the charge on this dot, you completely quench the spin orbit, so you don't even have to move the magnets. Okay, so so we like to do, so we can do things, different things, and different is different, so that's very interesting. And so now I'm going to show you that you can even achieve the strong coupling regime in a quantum dot circuit attached to superconducting leads. And this is very interesting because, for example, if you engineer non-local superconducting correlations, and this has, for example, to some extent, some connection to the recent efforts to gain topological superconductivity in these kind of systems. And so our favorite, let's say, elementary device where we engineer non-local superconducting correlations is a Cooper pair splitter, in which we have a superconductor which is attached to 2 quantum dots, and each of the dots being attached to normal leads. So, well, that's so in fact this gives essentially rise to a new low energy spectrum, which has because the superconductor now renormalizes the spectrum of the double quantum dot. And essentially, this gives rise to new ways to couple to the microwaves, because now the energy levels not only depend on the detuning between the left and the right dot, but since you're injecting and retrieving Cooper pairs, it depends also on the average. And since the microwaves shake much more the average than the difference, this gives rise to an extra, very strong coupling mechanism to the microwaves. Okay. So how do the device look like? That's the kind of device which we use. So that's a coplanar waveguide cavity. These are DC control electrodes. And simultaneously, we measure the transmission amplitude and phase through this microwave resonator at low temperatures with a cryogenic amplifier, and the conductance at low bias, at low frequency, which flows through this device. So here is how our Cooper pair splitter looks like. So here you have a single-wall carbon nanotube. So here you have the normal electrodes. That's a superconducting electrode. The 2 side gates which control the position of the energy levels on the left and the right. And this fork here goes to the central pin of the microwave resonator, and allows us to shake, let's say with the microwaves, the 2 energy levels simultaneously. So by doing this, what we have done is not only to couple a bit differently than what is done usually the system to the microwaves, but we have also strongly reduced the charging energy of the system. And this is very important because reducing the charging energy of the system means that you reduce the sensitivity of the internal transitions to the charge noise. And this is the main, let's say, decoherence mechanism in this kind of electrically controlled systems, which is usually hindering the demonstration of the strong coupling. And so by doing this very strong reduction of the charging energy, in fact, we reduce very strongly the sensitivity to the charge noise, and therefore we reduce the line width of the internal transitions. Okay, so we can characterize the system with transport. So we see here a map of the current flowing to the left or the right arm as a function of the gates. So it's a rotated essentially frame, but that's essentially the difference between the left gate and the right gate, and the sum between the left gate and the right gate. So here you see this kind of zoom, this kind of evaded crossing, which tells us that we hybridize states on the left and on the right dot. And if you measure the current, the conductance through the device, you see a well-defined gap which cuts the Coulomb diamonds. This tells us that we have indeed a superconducting interface. Okay. So now what is interesting is to look at where we have absolutely no current. So here, for example, and here, at the microwave signal. And so here's what we have. So this is for 2 different tunings. So what you see is that this dashed line here is highlighting these lines here, which we see in the current, and it's also a theoretical fit. So this, you see these dashed lines in the microwaves. This is normal because on these dashed lines, you can hop, the charges can hop back and forth. But what is very interesting is that when you have absolutely no current, you see a very strong microwave signal here with a phase of the transmitted microwave signal which changes sign. So it's a bit similar here. And in fact, that's exactly, so the dashed lines is what we expect from the low energy theory, from the spectrum which we have, I have briefly flashed you at the beginning. This stems from the spectrum of the device. So we have a quantitative understanding of the low energy spectrum of our device. But what is very important is that you see you have a very strong sign change here with large phase contrast. And even in some places here, in the amplitude, I mean, you have photon emission here. Because the amplitude gets larger, you have amplification. The amplitude of the microwave signal is larger than what you have put at the input. So these two things are actually characteristic of a coherent interface between the photons and your electronic system. And therefore, you expect to see, if you tune properly your system, a very strong departures from the let's say, the Lorentzian line width of the cavity if you measure the transmission spectrum of the cavity. And this is indeed what you have. So this is now for a different device than the previous one. If you tune now this device in resonance with the cavity, you see that you have a normal mode splitting at very small photon number of about 10 megahertz. This is the vacuum rabbit splitting of our system, which corresponds to the coherent coupling of our non-local superconducting system with the microwave photons. So what is very important is that here, since we deal with few-level system, we expect to be able to have a very strong power dependence of the transition. And therefore, for example, we expect some saturation effect when we essentially populate with a large number of photons the cavity. So this is indeed what we see. So that's for n equal to 1. And if we go to 400 photons, essentially we completely saturate the transition. We recover the purely Lorentzian line shape. And this we can understand quantitatively with a soft, which is called Q-tip, which allows us to calculate the full, power dependence of this kind of transition schema. And essentially, this gives us confidence that we are really talking to an harmonic microscopic system, and that we have not coupled accidentally to a harmonic oscillator our system, and this is why we have the vacuum rabbit splitting. So we indeed have coupled strongly our microwave cavity to, let's say, to the internal, spectrum of our hybrid superconductor quantum dot. Okay, that's the conclusion of part 1. I'm going to have to speed up. And essentially, the perspectives of this work is first that since we have a coherent interface between our electronic system and the microwave photons, we can imagine to have an ultra-long distance coupling between like a double quantum dot circuits made like these ones. And also you can imagine to generalize this kind of non-local, let's say, to this kind of coupling of non-local superconducting correlations to the topological regime to probe Majorana fermions in condensed matter. Okay, but now, so I told you that at the beginning that we, in fact, we will be willing to use also this architecture to understand more condensed matter questions, because the microwave cavity allows you to probe the compressibility of the system. And the compressibility is particularly interesting to probe when you have strong correlations. So, in fact, our favorite strongly correlated system is the Kontos problem. Problem is the Kontos problem. So, which occurs in magnetic alloys, like copper iron with 0.2% of iron. But the modern way of looking at the Kontos problem is through the Anderson model, where essentially we shows you how you can generate a finite, let's say, magnetic an impurity with a finite magnetic moment, and how this is screened at low temperatures by the conduction electrons. So that's a very, so the spin also here is important, of course, because you have interactions, and it's a very important many-body problem, because that's the simplest many-body problem on which you can say something. Okay, and so this, of course, can be emulated in essentially in quantum dots. And our favorite quantum dot in our case is also based on carbon nanotubes. So here's again the same architecture as what I have shown you before, a slightly different coupling scheme. So you have two normal electrodes here. This green electrode goes to the, is coupled to the central pin of the resonator here. And now, essentially, we measure simultaneously the conductance with throws through the system at low frequency, and the microwave response. And the microwave response allows us to directly probe the compressibility of the electronic system. Okay, so first we need to calibrate how sensitive we are for the compressibility. And essentially, in order to do so, what we want to do is to go to a very well-known regime. It's the Coulomb blockade regime. And essentially, this corresponds to tuning the gate voltage of our quantum dot in a certain regime where we have opaque barriers to the leads. So this is typically what we have for the conductance. So let's zoom on the conductance as a function of the gate and the source drain. So you have Coulomb diamonds, which repeat here with a structure of 4, I mean, if you would look on larger scale. And what you see here is that the Coulomb peaks here in the conductance are perfectly correlated to the phase, to the compressibility peaks. So that's somehow expected because these Coulomb peaks means that you're bringing into resonance a charge level with the leads, and this is where the charge can fluctuate. And therefore, this allows us, this is somehow expected, and this allows us to calibrate from the phase contrast the coupling strength, which we found to be sizable of about 100 megahertz. So now the electronic and photonic systems are well coupled. What about the Kontos regime? And so for the Kontos regime, we just have to tune to put the gate to more positive values. And when you put the gate to more positive values, you open the contact, so the gammas get bigger and bigger. So the Coulomb diamonds are more blurred. But what is very important is that you see a horizontal line here, which is a Kontos ridge. So if I do a cut, for example, along this dashed line, I see a peak at zero bias here, and bumps, which are charge fluctuations at large energy, which are essentially the discharging energy. So what is the compressibility associated to this peak here? So, and you see from the phase contrast that there is no compressibility associated to this peak here. So this means that, in a way, the Kontos resonance, even though this is a peak in the density of states, it's completely transparent to the cavity photons. So how do we understand this? It's well, we go back. I mean, to the let's say the original picture of the Kontos model. In fact, the idea is that in the Kontos, let's say, model, the spin is completely allowed to fluctuate back and forth. Through these virtual states, for example, but the charge, let's say, is completely frozen, is completely blocked on the energy level here. So this is really a cornerstone of the Kontos model, and therefore you open a channel at the Fermi energy of the leads, or in the density of states, and therefore you open a channel for the conductance. Although you have a completely frozen charge. So in other words, you get an electrical conduction from a frozen charge in this kind of system. And so this measurement essentially illustrates directly that essentially you have an incompressible state associated to this peak in the density of states. And this illustrates further the fact that essentially you separate, in a way, you decouple the spin and the charge dynamics in the Kontos system at low energy. And so this is very well reproduced by a numerical renormalization group, which has been done by Min-Chul Lee and Man-Soo Choi in Seoul. So you see similar things in the temperature dependence, essentially that the energy scales controlling the temperature dependence of the conductance and of the compressibility are completely different. So here this is the Kontos temperature, and here this is the gamma, so which is the coupling to the leads. This is also qualitatively reproduced by the energy data. And so all these data really directly illustrate that this peak in the Kontos cloud is associated to an incompressible state. Okay, so in the last part of this talk, I have shown you that the cavity are also good for understanding many-body physics because they allow you to probe some things, quantities which are completely different from the usual transport measurements. And in fact, they allow you to probe these quantities with very high sensitivity. And so this has allowed us to observe, like for the first time, the frozen charge of a Kontos resonance. And the perspective of the setup are, let's say, for example, you can imagine to shine a large number of photons in the cavity and to some kind of quantum quench of the Kontos cloud. And more generally, we like to think as this system as a quantum simulator of fermion boson problems. Thanks for your attention.